Swayam Prabha. Digital India. Educated India.
Okay, so now let us try to understand this inferencing at low precision. Okay, so again, here we'll start with the premise that the weights and activations which we used in during the training of our model was floating point 32, FP32, and it can be represented using int 8 without incurring significant loss in accuracy. This is a well-known fact which people have been trying since long, and it is possible to achieve this. So assuming that we know that when we convert our weights and activations from FP32 to int 8, we don't incur significant loss in accuracy. Okay, so this is one way of trying to reduce in the memory, but it has got its disadvantages. We will see what are the disadvantages and what are the advantages, and how do we ensure that the accuracy is maintained. Okay, now what are the advantages actually of doing this conversion from FP32 to int 8? What actually happens is when you do this, you can significantly reduce the bandwidth and the storage, and your integer compute, sorry, there's a typo here, it is basically integer compute is faster than the FP compute. Okay, and this also saves energy and area. So these are very important advantages, or very significant advantages. You reduce the bandwidth, you reduce the storage, your integer compute is faster than your floating point compute, and you save area and energy as well. So let's try to understand, if you do a add operation as a int 8 operation instead of a FP32 operation, you are going to save 30x energy and 116x area as against doing it on a floating point 32. And if you do a multiply operation using int 8, you're going to save 18.5x energy and 27x area versus floating point 32 operation. So now think of this, just for one add and multiply like operation, you are saving so much energy, so much area, and you are talking of deep neural networks which will use lot of such operations. You are talking of convolution neural networks, right? They are deep neural networks. You will have so many of such operations, and once you are able to reduce the energy, the area, okay, you will actually get, okay, lot of advantages in time as well. Okay, so the idea is that we should actually significantly use, okay, and try to use int 8 operations. So there are so many other things wherein people talk of mixed precision, right? Automatically the softwares can actually take in the required precision values and all of that, but we're not going into that. What I'm trying to tell you is if we do int 8 operations at low precision, we can get good inferencing, okay, as compared to if you just use FP32, right? Now, what does it mean when we say precision from FP32 to int 8? Where is the issue here? The issue is basically you are trying to do something called as quantization. If you are working with FP32, your dynamic range actually varies from minus 3.4 into 10 to the power of 38 to plus 3.4 into 10 to the power of 38. This is the dynamic range in which your model would have got some values, right? For the weights, for the activation. So that is the whole dynamic range which you are working with. And this is what is, let us assume, to be the training precision. So the training precision's dynamic range varies from minus 3.4 into 10 to the power of 32 to plus 3.4 into 10 to the power of 38. Sorry, 38, right? So minus 3.4 into 10 to the power of 38 to plus 3.4 into 10 to the power of 38. This is your training precision. Now, if you reduce it from FP32 to just FP16, your dynamic range changes from minus 65,504 to plus 65,504. What does it mean? The dynamic range of your information or the values which have varied from this particular range to this particular range has to be condensed into minus 65,504 to plus 65,504. Okay, so what does it mean? Here you are changing your precision from FP32 to FP16, your dynamic range reduces, right? So this basically means whatever information was put in that particular range should be compressed to this range, right? And there are softwares which are available which you try to use. This particular step does not require any calibration. So you don't require any calibration. Okay, we'll tell you what a calibration means in brief. Okay, why is it required? And when you convert the FP32 to int 8, okay, you basically have to work with a dynamic range of minus 128 to plus 127. So you would have trained your model with FP32 thinking that you have got this much precision, this much accuracy, right? And this is the uh, model which is giving me accuracy because I'm using floating point 32. And then now you try to convert it to int 8. You actually have to represent that information which you have thought from minus 128 to plus 127. And technically, this is where some calibration is required, right? We'll not discuss it in today's class. Maybe we'll tell you something about that in tomorrow's class. But the next class, the idea is this requires some calibration because you will have to map it from a very different dynamic range to a very small dynamic range of minus 128 to 127, right? So this basically means when you are trying to do this precision calibration for int 8 inferencing, it minimizes the information loss. Try understanding when you do the calibration, what effectively happens is we will minimize the information loss between FP32 and int 8 inference on a calibration data set. So there has to be a specific calibration data set designed before you convert your FP32 into int 8, and that calibration data set is going to ensure that your precision, your accuracy is not affected. And this will be done automatically, right? So it is completely automatic. Okay, now let us try to understand the difference in the performance or accuracy of various networks. Okay, so if you take FP32 and you consider top one results, okay, whatever top results you consider for anything. This is an example wherein GoogleNet gives you 68.87% accuracy. VGG gives you this. ResNet 50 gives you 73.11. ResNet 158 gives you 75.18. Now, when you do it using int8, you optimize your model, run it for inferencing. Okay, the int8 model gives you accuracy of 68.49 as against 68.87. So this is just a difference of 0.38%, right? The same is the case with VGG. You get a difference of 0.11%, 0.57% for ResNet 50, and 0.61% for ResNet 152. So the idea here is that there will not be much of a difference. Of course, you can still go on improving and optimize it further, but this is not that much of a difference, right? When you get the advantages of so many things like energy, bandwidth, storage, faster compute, okay, and everything. So this is what is basically the gist of inferencing at low precision, right? Okay, so in summary, let us try to understand what I have talked till now. So in essence, the summary is whatever we have done till now points to this. We are actually training this type of a model. Let us say it is trained with a lot of labeled data, and then you have got this forward propagation and then the backward propagation, error propagation, everything of that, and your training model is able to actually predict something, right? When you test it, when you do validation and everything. Now, when you actually bring this model weights for that inferencing edge device or deploy the device, or where you need to deploy, the inferencing is something like you give the input, it should give you the output. This particular system, right, for example, has to be implemented at traffic, some traffic situation, right, smart city situation. So you have, let us say, a traffic camera, you have a gateway server, and you have a data center. So the idea here is you have used and you have done training at the data center with GPUs, and let us say that this is a 300-watt AI training processor. What it does, it trains our AI model basically, which is used in basically traffic camera and the gateway servers. So that is the work. Once it has trained, it has to go for inferencing now, right? And what does it process? Let us say it processes the traffic violations. Okay, now what does gateway server do? Gateway server is a 50-watt AI inference processor. Here it is an inference processor with a 50-watt AI thing. What it does, it locates the license plate in vehicle image and it reads the license plate characters. That is what a gateway server is going to do. What does a traffic camera do? So a traffic camera is a 5-watt AI inference processor. So see, the same trained model, okay, is running on a 300-watt AI training processor, it's running on a 50-watt AI inference processor, and then it's running on a 5-watt AI inference processor. So in a 5-watt AI inference processor, the same trained thing, what it does, it detects the vehicle which is entering the intersection, it identifies the image that includes the license plate. So the inferencing here is done for this. The gateway server locates the license plate there and it detects the characters, and here it detects the traffic violation. So the idea is the level at which you are going to put in your model and the way in which it has to be used varies, okay? And the idea is that here you are going to use something which is trained and something which has to be put or deployed for inferencing, right? So now this is the actual example implementation. Let us show you actually how we have implemented it in our lab, right? So what we have tried to do, we have tried to train our model, right? Let us say we have used ResNet 50. Here we are not using NVIDIA digits, we are using ResNet 50. And ResNet 50 is basically trained, okay, on DGX1. So at this point in time, we have got a trained deep neural network model, which is a pre-trained model. Okay, and we have NVIDIA Jetson. We have got NVIDIA Jetson TX1, TX2. So we'll be showing you on TX1. Okay, now that basically is a uh, edge device, right? And this edge device basically is used for inferencing. What does it have? We have to be very clear that we are using TensorRT. Okay, we will tell you what TensorRT does, and we have CUDNN also installed on our Jetson kit. Okay, so the idea is this model, which has been trained for doing some classification tasks on the DGX, is now to be converted, optimized, made smaller so that it can run on this Jetson. Okay, now this Jetson actually is able to classify the objects, okay, based on the inputs from the camera in the real life setting. So this is what is the situation, right? This is what we are going to actually do a implementation for. Okay, so now let us try to understand the TensorRT thing, right? So what is TensorRT? I just showed you that we have something which is called as a TensorRT with CUDNN installed on our edge device. Edge device is nothing but our Jetson. Okay, there are various other edge devices also, but we are showing you with NVIDIA Jetson. Okay, so this NVIDIA TensorRT is a high performance deep learning inference optimizer and a runtime that delivers low latency, high throughput inference for deep learning applications, right? So what it means is we are trying to accelerate deep learning inferencing for production deployment. This is what is the basic essence. So whatever we were talking of all of this, okay, actually is taken care by this TensorRT. So the goal is that we would be accelerating deep learning inference for production deployment. Now what does it mean? See here, this is our training framework on DGX and all. Our neural network is trained. We use the precision, we use the batch size from this, we optimize it using our TensorRT, and then we generate a plan. Now this plan gives us a serial plan of plan 1, plan 2, plan 3, something like this. And then once we can validate it using TensorRT, we actually would be using it for actually predicting. Okay, so now why TensorRT and why it is required and how do we use it? Maybe we will see it in tomorrow's class. Now we can do a video demonstration of what we have done. I'll just explain you in brief what we have done, and let me just show you the images first. Okay, so see here, this is the output from the screen of our Jetson device. Okay, this basically tells us about what are our video output arguments, what is the codec we are using, what's the width, size, okay, what are my image files and all of that, right? And this is being shown on a setup like this. Okay, so this is our NVIDIA Jetson TX1. This is how it is running the program, okay, of various types, right? We have done some semantic segmentation programs, we have done classification, we have done detection. There's so many things which run on this, okay? Now the idea is once you start working on an edge device, you will try to understand that there's a difference in which uh, there's a difference in way your DGX does inferencing and the inferencing which this particular type of edge device does, okay? So there are 3 videos which I'll show you today, and maybe tomorrow we will see as to how that is to be achieved, right? So let us start with this video which talks of, okay, how you can get the information from the camera, okay, and then do things uh, and optimized from the TensorRT thing, right? We are using TensorRT version 7.1.3, and there are various things which you'll use. So this is basically trying to do some object detection, okay? Now here the idea is we have tried to link the hand to a person, okay? So that is what we did some modification. Just wanted to show you, like if you change the model, if you do the training in such a way, right, it can affect your inferencing a lot. So this is our Jetson TX1 which you're working with. Now this is another video which talks of trying to do detection, okay, of person, chair, okay, everything. So see the way in which it is detecting, right? The throughput rate, the speed at which it is detecting, the speed at which it is inferencing, right? All of this actually is being executed on this Jetson TX1, okay? So right, so this has got a small camera, okay, which basically we will show you tomorrow in detail, but this is the camera here which is trying to capture the image, right, of the person sitting here and here. So this is how actually we are trying to do this uh, thing, okay? So then there is another video which actually does how this convolution, okay, zero, ReLU, and everything actually, okay, gets converted and how much time it takes, right? All of that. I'm just trying to show you today so that the context is built so that you can actually try to understand things tomorrow in a better way, right? When we start working on trying to show you these executions. Okay, so this is how actually it will be processed, and that particular video uh, is actually going to be predicted, right? So that is how actually it is. So I should have maybe shown you this before than the other video which I showed just now. So that is how actually it is going to basically be executed, okay? And that is how you can develop in your own applications and put it on the edge device, right? So this is how actually it's going to pan out. Okay, so we have done it for cats, dogs. We'll show you tomorrow cats and dogs maybe. So let us see. So yeah, so I suppose uh, we are done with today's session. Yeah, maybe any questions if you have, we can start. So maybe yeah. So I'll just wind off with why TensorRT just to complete the whole thing. So what is actually TensorRT and why we should use TensorRT is it's a software platform for high performance deep learning inferencing. You actually get a trained neural network, you optimize it using TensorRT optimizer, and then you use a TensorRT runtime engine to actually run, right? So basically it's a software platform for high performance deep learning inference. It processes images faster. That's what will happen, right? So often you need to trade off between speed and accuracy, obviously, as we discussed. TensorRT based applications perform up to 40x faster than CPU only platforms during inferencing. So if you have a TensorRT based application developed, it's going to perform 40x faster than just the CPU only platforms. You can deploy it to hyperscale data centers, embedded or automotive product platforms as shown here. So you have Jetson, which we are working with. You have Drive AGX, which you can work with for automotive. And then you have Tesla, right? Basically on the data center. So this TensorRT, you can actually optimize your model and deploy it anywhere. That's what it means, right? So it will be optimized according to where it basically is running, right? So you can use the TensorRT for speeding up the recommender systems, speech processing, video translation. Now you can use actually this TensorRT to take advantage of tools like DeepStream and NVIDIA inference engines. You can do edge processing with NVIDIA Xavier, as I told you, Jetson TX1, TX2, and Jetson Nano, all three. Okay, so you can do everything using TensorRT, right? So it's a deep learning inferencing software platform, which we'll show you tomorrow in the next class, right? So yeah, I think I'm done now. We stop here. Yeah.